Welcome to springlib.
We want to describe how the graph of f of x is equal to x squared plus cx varies as c varies, and we're going to then graph several members of the family to illustrate trends that we discovered. And in particular, we want to investigate how our maximum, minimum, and points of inflection move as c changes. We also want to identify any transitional values of c at which the basic shape of the curve will change. So here, you can see I have the functions listed for c is equal to -1, or -2, -1, 0, 1, and 2. But before we look at these graphs more, let's just do a little bit of stuff with the general function. So the first thing you might notice is we could go ahead and factor this, because we can pull out a x. So we get x is equal to, or this is equal to x times x plus c. And if we were to go ahead and set this equal to 0, that's going to imply that either x is equal to 0 or x is equal to -c, just using the zero product property. So we know that no matter what, we will always have an x-intercept at 0, and for whatever value we choose for c, the negative of that will be our other x-intercept. All right, so that gives us a little bit of information. Now let's go ahead and look at the derivative of this. So f prime of x, because remember, to find maximum or minimum points, we can look at critical values, which is where our derivative is equal to 0 or undefined. So taking the derivative of x squared plus cx, we would use power rule. So x squared becomes 2x, and cx, well, c is a constant, so the derivative of x is just 1. So we just end up with 2x plus c. Now, to find our critical values, remember the thing we want to do, set this equal to 0. And that's going to imply that if we have any maxes or mins, it's going to occur at -c over 2. And you might recall that this here is just the vertex, because we're working with a quadratic. So we could have did the whole -b over 2a, plug those in to get the same point. So we know how our, in this case, is going to be a minimum, since we know our leading coefficient is larger than 0, or positive. We know how our minimum is going to change, because it's just going to shift to the left or to the right based off this value here, or at least the position along the y-axis, the x-axis is going to shift. I should say that. And now for our last part, let's go ahead and look at the second derivative and see if we can find any points of inflection. So f double prime of x is going to be just 2, because the derivative of 2x, well, derivative of x is 1, so we're just left with the 2, and the derivative of c, since it's a constant, will be 0. And we know that this here is strictly greater than 0, which is going to imply that our function is always concave up. So there should be no points of inflection. And if we just go through and look at these values, we can kind of see what we expect to occur from this little analysis does happen. So starting at c is equal to 0, which is this middle graph here, we can see when c is equal to 0, we get that our x-intercepts are only at 0. And if we were to go ahead and plug in 0 into -c over 2, we get x is 0, so our vertex is also there. Now, when c is -1, our vertex shifts down and to the right, as well as we get an extra x-intercept at 1, which is exactly what we would expect again When c is equal to -2, it shifts halfway in between those two values for c for our vertex. So it's now at 1, and we get our x-intercept over here at 2. And looking at c is equal to 1, x-intercept gets shifted to the left 1, and our vertex is right in the middle of those two. And c is equal to 2, same thing. Our other x-intercept gets shifted to -2, and our vertex is half that distance.